Hey guys, how's it going? If you pop in and you notice that the audio is all jacked up, please let me know. It wouldn't, to be honest, it just wouldn't work this morning. I'm testing some things and trying to track the audio. I will watch this afterwards just to give it a check to make sure that we're actually seeing the right stuff before we have a live session this afternoon. So one of the things I was thinking we could do this morning is we could look at titrations. Or if someone else has a question, I'm happy to answer that. Before we look at titrations, let's look at bond angles, because I think one of the things I've noticed is some of you guys are drawing structures where the bond angles are, you're basically just subbing out the wedges and dashes in your Lewis dot structure. It turns out that that's not actually correct. Your bond angles cannot be 90 degrees. So we should see bond angles of differing values. So let's, I remember the last time I tried to do this, it kind of collapsed on me, but we'll see how it goes today. It's happening. Things are coming along. Let's find out if it works. Plug this in here. Yes. Cancel. Not now. Now that. And then we're going to switch it. Yeah. So, bond angles. Let's talk about that. So when you draw a wedges and dash, so if we have a bond angle, your bonds in VSEPR. So if you have a tetrahedral molecule, such as methane, so that's CH4, we know that our Lewis dot structure is going to look like this. So we know that this structure has a steric number of 4. The steric number just means that we counted the number of things connected to our central atom. In this case, carbon is our central atom. So we need to draw a VSEPR structure. A steric number of 4 is tetrahedral. And a tetrahedral molecule has a bond angle of 109.5. So I'm not asking you to get out a protractor and measure exactly 109.5. But we know that it is greater than 90 unless that it's less than halfway between 98 and 180, right? So we're just asking for an approximation. So what I've seen some students do is this. Where you just swapped out the wedges, you added wedges and dashes. So this, it turns out, is wrong. And so the reason it's wrong is it doesn't tell us anything about the three-dimensional space. It turns out we learned nothing different between the structure crossed out in red and the structure in black, the Lewis dot structure. That's just not any new information. But if we draw it with approximately 109.5, what we'll see is we have carbon. Well, that's not the best line. And it looks like this. And so now what we see is our 109.5 degree angle is pretty close. So this, with wedges and dashes, this is VSEPR. And so when we see structures that look like this, we know that they are, I don't want to say necessarily, they're not perfect, but they are much, much, much better than this structure on the right, where we basically have a big red X because it didn't tell us anything. So this is true regardless of what your structure is. So there really aren't any 90 degree angles, even in an octahedral structure. So in an octahedral, this is steric number of 6, and we know that the bond angles are 90 degrees. But if we have our central atom, in order to delineate that they are 90 degrees, it turns out that while you could draw this structure with 90 degree angles, you could draw something that looked like this. It would be equally correct. So these two structures are basically just rotated, and the wedge and the dash tell you that in the case of the octahedral, it is pointing back and forth. So you would have 4 in a plane and then 1 in front and 1 behind. So that's really the only time we would see something with 90 degree angles. So these bonds are all 90 degrees in any case. So when we think about drawing these, this is what we're going to think about. So all of the structures don't really have 90 degrees, although the only one that does is our trigonal bipyramidal, which has this structure here. And what you can see is there is, in fact, a single, well, 2. These are 90 degrees, but these are 120 degrees. So when we look at this kind of information, we can start to say, like, okay, this makes sense. So what we don't want to see, what I don't want to see, is a large molecule drawn where you've just basically subbed it out and it looks exactly like a provided Lewis dot structure. If you're provided a large molecule, let's say acetic acid, which looks like this. So if you're provided a Lewis dot structure for something that is significantly larger, acetic acid in this case, and there are a bunch of other examples, we'll do one in the live session this afternoon, we can approach each individual central atom, so it would basically be this carbon, this oxygen. I'm going to erase those lines so that they don't confuse us. But those 3 structures, what we don't want to see is the following. What I will not give credit for is probably a more accurate statement, would be this. So this structure is wildly incorrect because it doesn't give us any new information than this Lewis dot structure that you can see in the top. So if this is our provided Lewis dot, this other one doesn't. So let's think about this in terms of something that makes probably the most sense. We know that this carbon right here has a steric number of 3, which is trigonal planar. We know that a trigonal planar bond has 120 degrees. So this should be 120 degrees, and you've drawn it as 90. But they're not even all the same. So we have 2 90s and 1 180, which does make a circle. So the thing is, we need anything that we can to be realistically drawn in a way that makes sense. So what does that mean? Let's try this again. So we can approach each one as it by itself, trying to do all of them at the same time. That just makes it complicated, to be quite honest. So instead, let's either start with the carbon on the left, so either this one or this one. You can pick either one. I tend to start with the one on the left, so let's do that. So we're going to have our carbon. We know that it is a steric number of 4, which means it's tetrahedral. So we're going to end up with a structure like this. Now, you can put it in any order, so the hydrogens can go anywhere, same with that carbon. I find that I would like the majority of my molecule to be in the plane of the paper. Why do I want that? Because if you draw something pointing out, you have to figure out where stuff goes in a new plane. I find that to be difficult. It's not impossible. You can definitely do it. So in this case, once we see this, we're going to add our carbon here, hydrogen, hydrogen, hydrogen. Now, this next carbon, carbon 2, is going to have a steric number of 3. We know that that means that it's going to have 120 bond angles. So I put the double bond oxygen at the bottom. You could have put them in either way. That would have been fine. David, the review session is at 3. These are just office hours. I'm just, frankly, I don't want to say talking to myself, just trying to make a resource. So at 3 o'clock, we will do the usual regularly scheduled live session. So next, we're going to add that second oxygen, which has a steric number of 4, because there are two pairs of lone pairs connected, a hydrogen and a carbon. So we know that that is going to end up with tetrahedral geometry. Now you could put your lone pairs on any of these, as well as the hydrogen. And now this molecule is what we would see if we could observe the structure or something pretty close to this in a spectroscopic method. So again, if you have a question, not a problem. I'm glad to help out, David. You can drop it in the chat box. If you don't, that's okay. I'll hang around for another couple of seconds. And then I will pop into my Zoom office hours. So if you have a personal, not a personal question, if you have other questions, you can find me there. So in a non-exam 3 topic, let us talk about titrations. So maybe 2 weeks ago, I think the last time we had YouTube office hours, I talked about limiting reactants. Today I want to talk about titrations. Titrations will show up on the final. If you already know everything there is to know about titrations, then this review is probably not all that exciting. However, for the rest of us, a titration is the ability to calculate an equivalent concentration at the middle point. So what we end up having is, let's say we have an acid plus a base, and that's going to give us salt plus water. And so we can have stoichiometric coefficients here that could be anything from 1 to 1, 2 to 2, 1 to 2, 1 to 3, 2 to 3. I don't want to say the options are endless, but the options are not just 0. So when we think about this, we know that at the equivalence point, which is the place where we're going to do the calculations. So we start at the beginning, then we go to the equivalence point. The moles of acid molecules equals the moles of base molecules. Now, this doesn't mean that we have 1 mole of H2SO4 and 1 mole of sodium hydroxide. That is not what this means. This means, so when we think about a titration, the acid molecule is in fact the acidic proton, and the base molecule is the OH group. In this case, the moles of acid and the moles of base, when we think about this, is equivalent. Now, if we have H2SO4 plus NaOH, gives us H2O plus Na2SO4. This equation needs to be balanced, and when we do that, we determine that we need 2's here and here. So at the equivalence point, there is the same moles of H2SO4 equals 2 times the number of moles of NaOH. Basically the stoichiometric coefficient. So it's not necessarily a mole to mole. We have to take into account stoichiometry. But in a titration, we can look at that in this way. So step 1. titrations just have 3 steps. So if we go back to H2SO4 plus 2 NaOH goes to 2H2O plus, yipes, no one wants to see that, plus Na2SO4. Now we have this compound. So step 1 is to determine moles of known. Usually, right, in a problem, it would say something like, oh, yipes, you can't even see that. Sorry about that. It would say, like, we started with 35 moles of 12 molar sodium hydroxide, 35 milliliters of 12 molar hydroxide, sodium hydroxide. What is the concentration if we used 10 mils of H2SO4? So from here, we would then go on to calculate this. So we'll determine the moles of known using volume and concentration. So step 2 is to convert moles of known to unknown. This, pretty simple, to be honest. The reason this is simple is we're going to use the stoichiometric coefficients. So we're going to say used balanced equation. So now we have the moles of our unknown. And then step 3, we want to determine the concentration. So when we do this, it is relatively simple. We're going to take the moles of unknown, divide by the volume of unknown. And that's it. But you'll notice that nowhere in this case did I use M1V1 equals M2V2. That is an acceptable shortcut. Never. So a lot of you like to use it because it's very simple and you feel like it gives you the right answer 100% of the time. If you used it in this case, it would in fact give you the wrong answer. There are ways that you can modify that and it might give you the right answer. There are some tricks and some different ways so you can. This is the way that I think works best 100% of the time. So this is all a titration is. And so I would provide 2 volumes and a concentration for one of those, and you can back calculate the concentration of the other. Titrations are scary because it feels like there's a lot of steps. When you break it into the step 1, step 2, step 3, it's not like way better, but it is much better than others. So on that note, I am going to go pop into Zoom in case anyone has questions. So y'all have a fantastic Monday, and I will see you in class.